All right, class. Hello. Um, I figured out how to get um, my computer, which doesn't have an Ethernet port, connected to my router through an Ethernet cable. I had to buy an adapter. And so, because of that, I think that my internet is faster now. And so, I think I can go back to the old way of doing things where I have two screens with my face and a picture of a piece of paper. Okay? So please let me know if it's not running smoothly, but I expect because I have a hardwire connection that it will be quite a bit smoother. Yeah, so that's good. I think I'm going to close the window here because someone has decided to start weed whacking just as I begin my lesson. All right, I'm back. I am sitting on the floor in front of my couch. So, today's lesson, here's what we were discussing yesterday. Yesterday we learned the wine displacement law, which says that the wavelength that most of the okay, so let me rewind a little bit. If you have a black body that's at a non-zero temperature, it's going to emit electromagnetic waves, and it emits all different electromagnetic waves, but most of the electromagnetic waves come out at a certain wavelength that depends on the temperature. So there's this formula. This is for the lambda of the peak. It's 2.9 times 10 to the minus 3 meters Kelvin over the temperature. Okay, so that is the formula for the maximum wavelength. Now, if we look at our brightness versus wavelength graph, it kind of looks like this. It's like an asymmetrical bell curve. Okay, and so if we were to calculate the area under the curve for this graph, that would be the total energy radiated away. Okay, by the black body. So that's all the wavelengths combined. That's the total energy radiated away. Hello, spicy pepper. So, and you might recall that if we raise the temperature, the peak, so this would be lambda peak right there. Turn this lamp off. Let me see if I can move this camera in closer. It's not as good quality as I want. Come on, camera. Yeah. There we go. Come on, focus. Okay. So if we were to raise the temperature, the peak is going to now be at a shorter wavelength. and the peak is going to be taller, like this. So we can see that if the temperature of the black body goes up, not only does the peak shift over, but the area under the curve gets bigger as well. So what I would like to talk about is a formula for the power radiated away by a black body. Okay, power radiated away by a black body. So there's a nice formula, and it says that the power radiated away is sigma A T to the fourth power. Okay, so P is the power radiated away. So remember, anything that has a non-zero temperature is sending out electromagnetic waves. So this is the energy carried away by those electromagnetic waves per time. Okay? A is the surface area of the object. Okay? More surface area means there's more surface to radiate energy away. So more surface area means more power is emitted. T is the temperature in Kelvin. Okay, so you can see that only when the temperature is 0 does something not emit any radiation. So, like I said, anything that's at a non-zero temperature is actually sending electromagnetic waves out away from them. So you're all like light bulbs. You're so bright in class. Notice that it's temperature to the fourth power. So that means that it depends, you get a little bit hotter and you get a lot more power radiated away. Okay? Sigma is called it's a constant of nature. It's called the StefanBoltzmann constant. Okay, because this is actually called the StefanBoltzmann Law. You don't need to know that, but it's called the StefanBoltzmann Law. And if you make your own law, you get to name the constant, I guess. And the constant is perhaps the easiest constant to remember in all of physics, in my opinion. It is 5.67 times 10 to the negative 8. 5, 6, 7, 8. Isn't that nice? And its units are watts per meter squared per Kelvin to the fourth. Okay? So that is the StefanBoltzmann Law. Okay? This lesson is brought to you by Dr. Pepper. All right. So now this is the equation for a perfect black body. If it is not a perfect black body, then the law is actually modified slightly. The power radiated away by a not perfect black body is epsilon times sigma A T to the fourth, where epsilon is a unitless number, and it's called the emissivity. Okay, and the emissivity is between 0 and 1. So the emissivity of a perfect black body is 1. And if an object is found to not obey the StefanBoltzmann Law perfectly, then we would say that it's not a perfect black body, and it has an emissivity that is less than 1. Okay? So different surfaces have different emissivities. It kind of depends on what the outer surface is made out of, what it looks like, the black body. Okay? So this is primarily the equation we're going to use. Okay? Let's do an example. Estimate the power radiated away by the human body how much power are you radiating away? How much energy is escaping through electromagnetic waves from your body? Okay, so here's a human being, and because the human being is at a non-zero temperature, they're sending waves out in all different directions. You're sending out electromagnetic waves. Okay, I'm going to represent a human being as a rectangular prism. So this is my model for you. You're just a block, a brick. And I'm going to say that you're a 2 meter tall brick. I'm going to say that you're 1 meter wide. And I'm going to say that you are 0.2 meters thick. All right? So what would be the surface area of this brick? Well, it would be 2 times, so the area equals 2 times height times width. So that would be the front area. Plus width times depth plus depth times height. Okay? So, all right? So let me calculate that. We get 2 times height times width. Now, do you guys understand why there's a factor of 2? It's because you have a front side and a back side, so those both add to your surface area. You have a left shoulder and a right shoulder, and you have a top and a bottom, basically. So that's why there's this multiplied by 2. Oh my gosh, I cannot believe how much yard work is just happening constantly. Is this happening in your neighborhoods too? I don't understand why yard work is an essential service that has to be happening right now. Okay, so we get 2 times 1 plus 1 times 0.2 plus depth 0.2 times height, which is 2. So this is 2 times 2 plus 0.2 plus 0.4. That's 2 times 2.6 equals 5.2 square meters. That's what I estimate to be the area of the human body. Okay. The temperature of the human body is, I believe it's roughly like 40 degrees Celsius. Anyone know what What is the temperature of the human body? Let me look it up. Temperature of human body, Celsius. Okay, it's more like 37 degrees Celsius. Knock it off, bug! Knock it off! Okay, and we want to convert that to Kelvin. So I'm going to add 273. It's 280. So that's what? 310 Kelvin is the temperature. And I'm going to assume that the human's body are perfect black bodies. Just sounds goofy to say. It's funny. Okay, so that means they have an emissivity of 1. So the power radiated away is epsilon times sigma times A times T to the 4th. So that's 1 times 5.67 times 10 to the negative 8 times the surface area, which we estimated as 5.2 square meters. Oops, 5.2. And the temperature is 310. And we raise that to the 4th power. So, got my calculator right here. 5.67 times 10 to the negative 8 times 5.2 times 310 to the 4th power. So that gets, wowie, that gives 2,722 watts. Okay? Now, I would say that that is a horrible estimate. And the reason why is that you might remember that this is a huge amount of power being output. So I would say this is not very realistic. And I would imagine that probably it's not very realistic because you are not a perfect black body. You have an emissivity that is less than 1, so it's probably quite a bit less than 1. I wonder if that, I'm going to look it up. What is the emissivity of the human body? It's right here. Look it. Yeah, it's less than 1. All right. The other thing that could be wrong with my calculation is I'm probably overestimating the surface area as well. So, yeah, this is too large of a power output. All right. So I think that's my lesson for today. So I'm going to go ahead and let you guys go, and go ahead and try out the daily item for today. Today's daily item is going to call back to our thermal physics, because you're going to have to figure out what is the temperature from the equation Q equals mc delta T. So keep that in mind. You're going to use the equation Q equals mc delta T. One other thing that I wanted to say is, if we take the law for the StefanBoltzmann Law right here, notice that if something is hot, it radiates away energy. So it's radiating away energy. Now guess what happens to the temperature as it radiates away energy? The temperature goes down. So as it radiates away electromagnetic waves, it gets cooler. And so slowly as it cools off, it radiates away less and less and less and less energy. Okay? So this is how things actually cool in outer space, is they slowly radiate away energy until their temperature approaches absolute zero. All right, that's my lesson for today. I hope you have a wonderful afternoon. Bye now.